In this video, we will define a very important quantity that's associated with a random variable, and it's called the mean. And we'll define what the mean of a random variable is, do an example, and then give you two different ways to kind of interpret what this number is, right? So let x be a discrete random variable. And what I'll do for now on is abbreviate random variable by RV, right? So not recreational vehicle, but random variable. So let x be a discrete random variable with the following PDF. Now, remember, when we have a discrete random variable, it can be discrete in one of two ways. Either it's finite, so that means our sample space consists of only finitely many elements, or it's countably infinite, which means there are infinitely many elements, but I can list them. They're discrete because they have gaps between them. So this definition that we're going to write down will cover both cases, right? So let's say we have, remember this is kind of our notation for the PDF. So we'll have that little x, and then the probability that our random variable takes on the value. So let's say x1 is the first possible value of x, and then it has a probability of p sub 1, and then let's say x2 is the next possible value of x, and we know there has to be a gap between them because of the discrete nature of the random variable, with the probability of p2, and then x3, and then it has a probability p3, and then let's just say and so on, meaning it maybe the list comes to an end, or maybe it's actually infinite, right? So here I'm just describing the PDF in the form of a table. So we have this. Now we define the mean of x to be this following summation. Now, one notation for the mean is to use the Greek letter, the lowercase mu. And sometimes you put the name of the random variable as a subscript just to, in case there's any kind of ambiguity. So you would say the mean of x, and this is how it's defined. And it's a sum. And what are you summing up? Well, what you do is you take each possible value of x, multiply it by its associated probability. So you multiply each of these pairs and then add them up. So let me say it like this. So it's going to be xi times pi, and the summation is over all the x's. So what I'm not going to do is put like specific limits, because I don't know if the summation is finite or if it's actually like an infinite series. So, but what I will say here is that the summation is over all xi's, and these xi's are the possible values in our sample space, right? And this is an important definition, and this is our mean of x, right? So let's do a very simple example to show the calculation, and it's a very simple calculation. And then what I will do is give you two ways to kind of interpret what this number means, right? So let's do an example here, And I'm just going to give a fairly simple PDF. And I'll make sure that this one is finite. So we won't get into the infinite series ones right now, right? So let's look at an example. So let's say this is our PDF. X can take on one of four values. 1, 2, 3, 4. And then here are the associated probabilities that it will take on these different values of X. So the probability that a random variable is equal to 1 is 0.1. The probability that it's equal to 2 is 0.3. The probability that it's equal to 3 is 0.2. And the probability that it's equal to 4 is 0.4. All right. So there we have our PDF. And now let's compute the mean, right? So the mean of X, which we can, in this case, since there's only one random variable in this problem, we could just call it the mean, which is mu. And so let me, now that I know that there are only four possible values of X, I can write this. Say k going from 1 to 4, and then it will be your xk times the associated probability, right? So this is what it would look like now if I knew exactly how many elements are in the sample space. And then again, the idea is that we're going to multiply these corresponding values, these pairs of numbers, and then add them together. And let me just say before we write this down, for those of you who are familiar with a dot product, do you realize that's kind of what you're doing? You know, if you think of this as a vector and this as a vector, and if you're doing the dot product, you're multiplying the corresponding entries and then you're adding them together, right? So I just wanted to mention that. So let's take the first possible value of X times its associated probability, and then the second value of X times its probability, plus the third value of X times its probability, and then finally the fourth value of X times its probability, right? So let's see what we have here. This is 0.1 plus 0.6 plus another 0.6 and then plus a 1.6. So add those four together and we will get 2.9. Right? There we go. So you couldn't ask for an easier sort of process as far as finding the mean of a discrete random variable. But then the question is, what does this 2.9 really mean? Right? So here are two ways that we can interpret the mean of a discrete random variable. So here are two interpretations. So the first one is kind of a physical one. And going back to that graph, like one graphical representation of a discrete random variable was that probability like line chart. But what I'm going to do is, let's say we have our number line here. And that number line covers, and these are the possible values of X. Right? So let me actually take these off. And so this is at 1, this is at 2, this is at 3, this is at 4. Now imagine that these dots are actually point masses on like a horizontal axis. And what we would like to do is to find the location of like a point of balance. So again, let's say that these are masses here, and let's say the mass at x equals 1 is 0.1. So maybe you can think of it either mass or weight. It's fine, right? So let's say there's a mass of 0.1 at x equals 1, and then there's a mass at 0.3 at x equals 2, and then there is a mass at x equals 3 of 0.2, and then finally there's a mass of 0.4 at x equals 4. If I were to put my point of balance exactly at x equals 2.9, which is my average, so if I put a little, I guess you could call it like a fulcrum, like right here, right? That location, if I put it at the location that's exactly equal to my mean, then this system will be in complete equilibrium, right? So one physical interpretation is that if the xi's represent the location of masses equivalent to the pi's, so of masses equivalent to pi, then the mean, which is our mu, represents the point of balance of this physical system, right? So represents the point of balance of this system, right? In other words, the system will be kept in perfect equilibrium if I have my fulcrum right there. If it's not, it's just like a teeter-totter, like with no one else sitting on either end. If I have it balanced right at that point, then it will be in perfect equilibrium, right? If I put it somewhere else, then it's going to be out of balance and so forth, right? So that's really an interesting way to look at the mean. And quite often in your like intro probability course like this is, you often don't see this interpretation. But I think this is a good one, particularly if you're an engineer or a computer scientist. This kind of physical way of interpreting, like what could this number really represent, right? Now, there are other things that you can um, interpret this number as, right? But this is a really easy one, right? So that's our first interpretation. The second interpretation is it's more of a statistical one, and this one says, now remember, the whole idea of probability is based on a random experiment, right? And again, what we're saying is we have an experiment and we associated all the outcomes with these numbers. And these are the possible numbers. So the possible numbers are 1, 2, 3, 4. So each time we perform the experiment, we will get one of these four numbers, right? So let's say we perform many, many trials. So perform not just once now, but many trials of this experiment. And each time we perform the trial, we're going to keep track of the number that we observe, right? So, and what I'll do is I'll write this. So these are now observed values. So like we actually go out there and perform this experiment. So it's not all hypothetical now. So what if, let's say we observe a 2, and then a 2, and then a 1, and then a 4, and a 4, and a 3, and a 3, and a 1, a 4, a 2, and so on. Well, the longer we perform this experiment, we will have a larger set of observed values. And if you take the average of these, so now let's kind of write these. Let me write it down symbolically. So the observed value, so x1, x2, x3, and so on, all the way, let's say, up to xn. So if I were to take the average of these n numbers, this is what they would look. This would be the calculation. So the average of the observed is, well, we know how to compute an average. It's just a arithmetic, so you take the sum and you divide by however many of them. So you'll have x1 plus x2 dot 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 plus xn, all divided by n. Well, what happens is the larger our set of observed values, so the longer we actually run this experiment, and again, keep dividing by n, what happens is this average will get closer and closer. It will actually converge to our theoretical value of the 2.9 that we just computed, right? So in other words, as n goes to infinity, this sum, in fact, let's write it with the sigma notation. So this sum, say k going from 1 to n of x sub k over n, this, which would be like your observed average, will converge to the mean of your distribution, right? And we sometimes refer to, because of this way of interpreting the mean, we sometimes refer to it as like the expected value or the average value of our random variable. So on average, we would expect, if we were to perform the experiment many, many times and take an average of the values that we observed, the larger the number of observations we have, the closer our observed average is to our expected value, right? So as n gets very, very large, this average will get closer and closer to the mean that comes from our PDF, right? And so for this reason, so mu of x is often referred to as the expected value, right? But it's expected in the sense that it's a long-term average. So over a long period of time with many, many trials, we would expect that on average, the values will get closer and closer to this mean, right? So mu of x is called the expected value of a random variable x, right? And then because of that, there's another notation that we use. So we just abbreviate expected with the letter E, and it's often written as big E of x, right? So in summary, this is what we have. right? So in summary, our mean, which is often denoted like this as well, the expected value of x, is defined as that summation, where it's the sum of all the xi's times the associated probability over all possible values of x. And again, there are two ways to interpret it. I think the first way is probably an easier thing for you to grasp conceptually in terms of these point masses that are located on some horizontal axis, and you're trying to find where do I establish this point of equilibrium, right? Or to place the system in equilibrium, and it's exactly what the mean of the random variable is. The second way is more of a statistical thing where you actually go out, right? And you say, if we were to perform this experiment many, 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 many times, and each time we do it, we just recompute our average observations. That average that we compute will get closer and closer to this theoretical mean. So it's really just a way of coming up with these observed averages that get closer and closer to what the theoretical model predicts. All right, so that's the mean. Now, just from a computational standpoint, it's very, very basic. But think about these ways of interpreting it, and it will help us going forward. See you then.